93 million miles away, a silent fire has been burning for 4.5 billion years. NASA has spent decades building machines just to peek inside it. Not the surface, not the flares, the actual core. The place where light itself is born. What they found down there changed how we understand our own star. This is the story of the sun's hidden heart. Every second, that fire keeps you alive, whether you notice it or not. But almost none of what happens in the core ever reaches your eyes. Because sunlight of you see today started its journey thousands of years ago. Yes, thousands of years, trapped inside the sun before ever escaping. That single fact took scientists over a century to prove. And it's only the beginning of what NASA uncovered. To understand the discovery, you first have to understand the mystery. For most of human history, the sun was simply a bright disk in the sky. Ancient civilizations worshipped it, tracked it, and feared its power. But nobody knew what actually made it shine. Wood burns out. Coal burns out. Stars should not still be burning. If the sun burned like a campfire, it would have died long ago. So something else, something far more powerful, had to be happening inside. NASA's mission was to find out exactly what that something was. The sun is not a solid ball, and it has no hard surface at all. It's a giant sphere of plasma, held together by its own gravity. Its diameter stretches over 860,000 miles. You could fit more than 1 million Earths inside its volume. And yet, everything visible to us is just the outer skin. Beneath that skin lies a churning ocean of superheated gas. And beneath that ocean lies the core, the true engine of the sun. The core makes up only about a quarter of the sun's radius. But it holds nearly half of the sun's entire mass. The pressure there is more than 200 billion times Earth's atmosphere. Temperatures in the core reach roughly 27 million degrees Fahrenheit. At those pressures and temperatures, atoms behave in ways nothing on Earth does. Electrons are stripped completely away from their atomic nuclei. What's left is a soup of bare protons and free electrons. Scientists call this fourth state of matter plasma. It conducts electricity, generates magnetic fields, and reacts violently to heat. Inside that plasma soup, something extraordinary quietly takes place. Hydrogen nuclei are slammed together with unimaginable force. And when they merge, they become something new: helium. This process is called nuclear fusion, and it releases enormous energy. It's the same reaction scientists have tried to recreate for clean energy on Earth. Except the sun does it naturally, every second, without any machinery. Every second, the sun fuses about 600 million tons of hydrogen. Out of that, about 4 million tons is converted directly into pure energy. That's Einstein's famous equation, E equals mc squared, playing out in real time. 4 million tons of mass, disappearing into light and heat, every single second. And it has been happening, uninterrupted, for 4.6 billion years. For a long time, this was theory, not proof. Scientists believed fusion was happening, but nobody could see inside the sun. You cannot drill into a star. You cannot send a probe to its core. Even light from the surface takes over 8 minutes just to reach Earth. So how do you study something you can never physically touch? NASA's answer was to build tools that could listen instead of look. And what they heard would surprise even veteran astrophysicists. The first breakthroughs actually came from studying tiny, ghostly particles. Particles called neutrinos, produced deep within the fusion reactions of the core. Neutrinos are so small and strange, they pass through solid matter like it's empty space. Billions of them pass through your body every single second, right now. They come from the sun's core and reach Earth in about 8 minutes. In the 1960s, physicist Raymond Davis built a detector deep underground to catch them. He placed it in a mine, shielded from cosmic interference, to catch solar neutrinos. His detector found neutrinos, but far fewer than theory predicted. Only about a third of the expected number ever showed up. This became known as the solar neutrino problem. For decades, nobody knew if the sun's models were wrong or the physics was wrong. Some worried the accepted picture of the sun's core might be incomplete. Others suspected neutrinos themselves were doing something nobody expected. It took until the early 2000s to finally solve the mystery. Scientists discovered neutrinos change identity as they travel through space. They oscillate between 3 different types on their journey to Earth. Earlier detectors were built to catch only one of those types. Once new detectors could catch all 3, the missing neutrinos reappeared. The numbers finally matched the models of the sun's fusion core. This confirmed, once and for all, that fusion really was happening exactly as predicted. It was a landmark moment in both astrophysics and particle physics. But neutrinos were only one piece of NASA's investigation. To understand the whole core, scientists needed another approach entirely. That approach came from something you'd never expect: sound. The sun, it turns out, constantly vibrates like a ringing bell.
These vibrations are caused by roiling plasma deep inside the star.
They create sound waves that ripple across the sun's entire surface. Scientists call the study of these waves helioseismology. It works similarly to how geologists study earthquakes to map Earth's interior. Sound waves traveling through the sun bend and bounce, depending on what they pass through. By tracking those patterns, scientists can map the sun's hidden internal structure. NASA's Solar and Heliospheric Observatory, called SOHO, was key to this research. Launched in 1995, SOHO watched the sun nearly non-stop for decades. It tracked subtle surface oscillations caused by waves from deep inside. Later, NASA's Solar Dynamics Observatory expanded this work even further.
Solar Dynamics Observatory has watched the sun in stunning detail since 2010.
It captures images of the sun every 12 seconds, non-stop.
That's an enormous, continuous data set for scientists to study. Using helioseismology, researchers mapped how fast different layers of the sun rotate. And what they found was completely unexpected. The sun does not rotate as one solid, uniform object.
Its equator spins faster than its poles, a phenomenon called differential rotation.
But inside the core, rotation behaves differently still. The core appears to spin, almost like a rigid, separate body. This suggested the deep interior and outer layers are somewhat decoupled. It hinted at complex physical processes scientists hadn't fully anticipated.
These findings reshaped models of how the sun generates its magnetic field.
And that magnetic field turned out to be far more important than anyone guessed. The sun's magnetic field controls almost everything about its behavior. It drives sunspots, solar flares, and massive eruptions called coronal mass ejections. Scientists believe this magnetic field originates from deep inside the star. Specifically, from the boundary between the radiative zone and convective zone. It's called the tachocline, and it may act like a magnetic dynamo. Differences in rotation speed twist and stretch magnetic field lines there. Over time, this twisting builds enormous magnetic tension. Eventually, that tension releases in bursts we see as solar activity. This cycle repeats roughly every 11 years, known as the solar cycle. During solar maximum, the sun becomes wild with flares and eruptions. During solar minimum, it becomes comparatively calm and quiet.
NASA wanted to understand not just the surface effects, but their deep root cause. That search led to one of NASA's boldest missions ever attempted. In 2018, NASA launched the Parker Solar Probe toward the Sun itself. It was named after physicist Eugene Parker, who first predicted solar wind. No spacecraft had ever dared fly this close to a star before. Parker's solar probe would eventually pass through the Sun's outer atmosphere. That outer atmosphere is called the corona. Getting there required surviving heat and radiation no craft had faced before. Engineers built a heat shield made of reinforced carbon-carbon composite. The shield can withstand temperatures around 2,500 degrees Fahrenheit.
Behind that shield, instruments stay at a comfortable room temperature.
In 2021, Parker Solar Probe made history by flying through the corona.
For the first time, a human-made object touched the Sun.
It sampled solar wind particles and magnetic fields firsthand.
Scientists discovered structures called switchbacks, sudden zigzags in the magnetic field. These switchbacks may be clues to how solar wind gets accelerated. They also may connect directly back to activity deep inside the Sun. Parker Solar Probe continues its journey, getting closer with each orbit. Eventually, it will fly within about 4 million miles of the Sun's surface. That's closer than any object humans have ever sent into space.
Every pass gathers new data about the forces shaping our star. But even Parker Solar Probe cannot see directly into the fusion core.
No spacecraft ever will, because the interior is simply too dense for light or instruments. That's why neutrinos and sound waves remain scientists' best windows inward. And what those windows reveal keeps surprising even veteran researchers. One surprising discovery involves something called the solar convection zone. This layer sits above the core and radiative zone, closer to the surface. Here, hot plasma rises, cools, and sinks in massive looping currents. It behaves similarly to boiling water on a stove, but on a colossal scale. These currents carry energy from deep inside outward to the visible surface. It can take hundreds of thousands of years for that energy to travel outward. That's why neutrinos carry the freshest, most direct evidence from the core. Light, by contrast, is delayed, scattered, and transformed along its long journey out. This is one of the strangest facts about our own star. The sunlight warming your skin today began its journey long before recorded history. It bounced, scattered, and absorbed repeatedly on its slow climb to the surface. Only in the final moments does it escape as visible light.
Neutrinos, meanwhile, carry a nearly real-time signal from the fusion reactions themselves. This is part of why NASA and partner agencies invested so heavily in neutrino research. It gave scientists a direct, almost live readout of the sun's furnace. Combined with helioseismology, it painted the clearest picture yet of the solar interior.
Layer by layer, scientists built what's now called the Standard Solar Model.
This model describes the sun's temperature, density, and composition at every depth.
It's been tested and refined for decades, using every tool available.
And remarkably, it matches observations with incredible precision.
This precision lets scientists confirm predictions once considered purely theoretical.
It proved the fusion process powering the sun follows what's called the proton-proton chain. In this chain, hydrogen nuclei fuse step by step into helium.
First, two protons combine to form a nucleus called deuterium.
Then deuterium combines with another proton to form a light isotope of helium. Finally, two of those light helium nuclei combine to form ordinary helium. Each of these steps releases small bursts of energy and particles.
Multiply that by unimaginable numbers of reactions happening simultaneously.
The result is the steady, powerful glow we call sunlight. This entire chain depends on extreme pressure and heat to overcome natural repulsion.
Protons naturally repel each other because they carry the same electric charge.
Only the sun's crushing gravity creates conditions strong enough to force them together.
Quantum mechanics also plays a subtle, crucial role in making fusion possible. A strange effect called quantum tunneling allows protons to fuse more easily than expected. Without quantum tunneling, the sun's core wouldn't be hot enough for fusion at all. This detail alone shows how deeply strange and delicate stellar physics really is. NASA's research didn't just confirm old theories, it uncovered new subtleties as well. For instance, scientists refined estimates of the sun's exact chemical composition. Around 3/4 of the sun's mass is hydrogen. Nearly 1/4 is helium, mostly created by fusion over billions of years. The remaining sliver includes oxygen, carbon, neon, iron, and other trace elements. Interestingly, measurements of these elements sometimes conflict with theoretical models.
This mismatch is known among scientists as the solar abundance problem.
Solving it may require even deeper insight into the sun's core chemistry.
It shows that even after a century of study, mysteries still remain.
NASA continues refining its instruments to chase these lingering questions. One tool used for this work is the Solar Neutrino Observatory Network worldwide. Facilities like Sudbury Neutrino Observatory in Canada helped confirm neutrino oscillation. Borexino in Italy directly measured neutrinos from specific fusion reaction steps. These experiments let scientists test the proton-proton chain, reaction by reaction. Each result added another piece to the puzzle of the sun's inner workings. NASA collaborates closely with international partners on many of these projects. Solar science, more than most fields, depends on global cooperation. No single country or agency could unravel the sun's secrets alone. This collaborative spirit has produced some of astronomy's most important discoveries. And each discovery reshapes how scientists think about stars across the universe. After all, the sun is our only up-close example of a typical star. Everything learned here helps astronomers understand distant stars they can never visit. If scientists understand how our sun fuses hydrogen, they understand countless other stars too. This makes the sun a natural laboratory sitting right in our own backyard. It's close enough to study in extraordinary detail, unlike any other star. Yet it's still nearly 93 million miles away, a safe scientific distance. That balance makes it uniquely valuable for astrophysics research. NASA has treated the sun almost like a long-term science experiment. Multiple missions have run in parallel, gathering different types of data. The Interface Region Imaging Spectrograph, or IRIS, studies the sun's lower atmosphere. It focuses on the mysterious region between the surface and outer corona. This region is where energy transfer becomes especially complex and turbulent. Other missions like Hinode, a partnership with Japan, studied magnetic activity closely. Together, these missions built layered, complementary views of solar behavior. But the deepest layer, the fusion core, still required indirect detective work. Every neutrino caught, every sound wave measured, added another clue. Slowly, piece by piece, scientists assembled a coherent story of the core. That story begins with immense gravitational collapse, billions of years ago. A cloud of gas and dust gathered and compressed under its own weight. As it compressed, pressure and temperature rose dramatically at its center. Eventually, conditions became extreme enough to ignite nuclear fusion. In that instant, a star was born, and our sun began to shine. That process happened roughly 4.5 billion years ago. Since then, the core has been steadily converting hydrogen into helium. Over time, helium accumulates at the very center of the sun. This changes the core's composition and, slowly, its structure as well. Scientists predict this gradual shift will eventually alter the sun's future. In about 5 billion years, hydrogen fuel in the core will run low. When that happens, the sun's structure will change dramatically. It will expand into what's called a red giant star. Its outer layers will swell outward,
possibly engulfing nearby planets.
Understanding the core today helps scientists predict that distant future accurately. It also helps them understand stars currently at different stages of that same process.
Some stars observed by NASA telescopes are much older than our Sun.
Others are much younger, still in earlier phases of their own core fusion. By comparing them, scientists build a timeline of stellar evolution across the galaxy. The Sun's core essentially serves as a calibrated reference point for that timeline. This is part of why NASA invests so heavily in solar research specifically.
It isn't only about understanding one star. It's about understanding all stars.
And by extension, it's about understanding the conditions that make life possible.
Stars, like the Sun, forge many of the elements found in living things.
Carbon, oxygen, and other essential elements trace back to stellar fusion processes.
In a very real sense, solar physics connects directly to human biology. Understanding the core isn't just abstract science, it's understanding our own origins. This connection is part of what makes solar research so compelling to the public.
NASA scientists often describe studying the Sun as studying ourselves, indirectly.
Every discovery about fusion adds a piece to that larger human story. And every mission adds new tools for uncovering deeper secrets. One especially exciting frontier involves predicting solar activity more accurately.
Because the Sun's magnetic behavior directly affects modern technology on Earth.
Solar flares can disrupt satellites, GPS systems, and power grids.
Coronal mass ejections can send charged particles toward our planet at high speed. In extreme cases, these events can damage electrical infrastructure significantly.
The famous Carrington event of 1859 caused telegraph systems worldwide to fail. A similar event today could cause far more widespread technological disruption. This is why understanding the Sun's inner workings has real, practical stakes.
If scientists understand the core's magnetic dynamo, they can better predict surface eruptions.
Better predictions mean better early warnings for satellites and power systems.
NASA's solar research, therefore, blends pure curiosity with practical planetary protection. It's simultaneously about deep cosmic mystery and everyday technological safety. Few areas of science combine those two goals so directly. This dual purpose has helped sustain decades of consistent funding and interest. Missions like SOHO, SDO, and Parker Solar Probe reflect that sustained commitment.
Each mission builds on lessons learned from the ones before it. Together, they represent one of the longest continuous scientific investigations in history. And still, new questions about the core keep emerging.
One ongoing question involves subtle irregularities in the Sun's rotation patterns.
Some data suggests unexpected shifts occurring near the core radiative zone boundary. Scientists aren't yet certain what causes these irregular patterns. It may involve magnetic interactions not yet fully understood. Or it could reveal something entirely new about stellar interiors. NASA continues gathering data specifically to investigate this open question. Another mystery involves tiny fluctuations in neutrino output over time. Some studies hint in these fluctuations might correlate with internal solar activity cycles. If true, it would mean the core itself has cycles, not just the surface. This idea remains debated among solar physicists today. Testing it requires extremely precise, long-term neutrino measurements. Facilities around the world continue refining their detection sensitivity for this purpose. Each improvement brings scientists closer to resolving the debate. It's a reminder that even well-studied stars still hold surprises. The Sun, despite being observed for millennia, remains far from fully understood. Every new instrument reveals details invisible to previous generations of scientists. This is part of the enduring appeal of solar research for NASA. There's always another layer, another signal, another subtle pattern to investigate. And each layer brings scientists closer to a complete picture of stellar physics. It also brings surprising philosophical weight to a purely physical process. Because fusion in the core connects directly to the concept of stellar lifespans. Stars are born, they live by fusing elements, and eventually they die. Our sun's entire existence depends on the specific balance happening in its core right now. That balance between gravity pulling inward and fusion pushing outward is called hydrostatic equilibrium. If gravity ever won completely, the sun would collapse in on itself. If fusion ever overwhelmed gravity, the sun would expand uncontrollably. For billions of years, these two forces have remained in near-perfect balance. This balance is what allows stars to shine steadily for so long. Understanding this equilibrium was one of NASA's major theoretical achievements. It combined nuclear physics, thermodynamics, and gravitational theory into one unified model. That model now underpins much of modern astrophysics as a whole.
It also helps explain why stars of different sizes behave so differently.
Larger stars burn through their fuel much faster than smaller ones.
Some massive stars live only millions of years before exhausting their cores. Smaller stars, meanwhile, can burn steadily for tens of billions of years.
Our sun sits comfortably in the middle, a stable, medium-sized star. This stability is part of why life had time to evolve on Earth. A star that burned out quickly wouldn't have given life enough time to develop. In that sense, the sun's core fusion rate quietly shaped our entire existence. This is one of the most profound implications of solar core research. It links nuclear physics directly to the story of life on Earth. NASA scientists often highlight this connection when explaining why the research matters. It transforms an abstract physics problem into a deeply personal cosmic story. Every discovery about the core adds context to humanity's place in the universe. And it all began with simple questions asked centuries ago. Early astronomers wondered why the sun never seemed to dim or fade. Later, scientists wondered what fuel could possibly last so long. 20th century physicists finally connected fusion theory to stellar energy production. NASA then built the tools to test and confirm those theories directly. Each generation added a new layer of understanding to the story. And each new NASA mission adds another chapter still being written today. Right now, Parker's solar probe continues gathering data closer to the sun than ever. Its measurements of magnetic switchbacks may soon connect directly to core dynamics. Meanwhile, helioseismology data keeps refining our picture of internal rotation.
Neutrino detectors worldwide continue confirming details of the fusion chain. Each data stream feeds into models scientists constantly update and improve.
This ongoing process shows science not as a finished answer, but an evolving story.
The sun's core, once a complete mystery, is now remarkably well understood.
Yet many specific details remain active areas of research and debate.
This combination of deep knowledge and remaining mystery is what makes the story compelling. It shows how far human curiosity and engineering have taken us. From ancient sun worship to spacecraft flying through the sun's atmosphere. From simple observation to precise measurements of subatomic particles. From guessing what powers the sun to confirming exact nuclear reactions. It's a remarkable journey, spanning centuries of human curiosity.
And NASA has been at the center of its most crucial chapters.
Its missions transformed the sun from a mysterious light into a measurable machine. A machine following precise physical laws, even at unimaginable scales. Laws involving gravity, quantum mechanics, and nuclear physics working together. All converging inside a core smaller than a quarter of the sun's total size. Yet that small region powers everything we see when we look at the sun. Every photon of visible light traces back to reactions happening there. Every bit of warmth reaching Earth's surface began in that same core. Every plant that grows, every ecosystem that thrives, depends on that distant fusion. In a very real way, that tiny core sustains life across an entire planet. This is part of why NASA considers solar research a top scientific priority. It's not simply about understanding a star. It's about understanding our life support system,
Few other research areas carry such direct relevance to human survival. And few offer such a striking blend of mystery and precision.
NASA's neutrino research proved theoretical predictions with stunning experimental accuracy. Its helioseismology research revealed rotation patterns nobody expected to find.
Its spacecraft missions touched the Sun's atmosphere for the very first time.
Each achievement added another confirmed fact to our understanding of the core. Together, they form one of modern science's most complete success stories.
But scientists are careful to note, the story isn't finished yet. Open questions about magnetic dynamos, neutrino cycles, and rotation anomalies remain. Future missions will likely refine and possibly challenge current models further. NASA continues planning new instruments specifically designed to probe these mysteries. Some proposed missions aim to measure solar neutrinos with even greater precision.
Others aim to map magnetic fields even deeper within the convective zone. Each new mission builds directly on decades of prior research and technology. But this layered, cumulative approach is how major scientific breakthroughs actually happen. Rarely through a single sudden discovery, but through steady, accumulated evidence.
The story of the Sun's core reflects that pattern perfectly.
Decades of neutrino detection, seismology, and spacecraft data all converged together. Each piece supported and refined the others, building a coherent picture. That picture now stands as one of astrophysics' most well-supported models.
It describes a core burning steadily at 27 million degrees Fahrenheit.
A core under crushing pressure, fusing hydrogen into helium every second. A core releasing energy that takes hundreds of thousands of years to reach the surface. A core sending neutrinos racing to Earth in just 8 minutes.
A core whose rotation patterns still puzzle scientists studying it today.
A core whose magnetic influence shapes solar storms, threatening modern technology.
A core that connects directly to the chemical elements found in living things. And a core that will, 5 billion years from now, transform the Sun entirely. This is what NASA found when it looked deep within the Sun.
Not a single dramatic secret, but an intricate, evolving scientific story. A story built from ghostly particles, subtle sound waves, and daring spacecraft. A story that connects ancient curiosity to cutting-edge modern instruments. A story still being written with every new mission and measurement.
It reminds us that even something as familiar as the Sun holds deep mystery.
Something we've watched rise and set every day of human history. Yet something whose inner workings took over a century of dedicated science to reveal. NASA's journey into the Sun's core stands as one of humanity's great scientific achievements. It combined physics, engineering, and sheer persistence across generations of researchers. And it continues today, with spacecraft still flying closer than ever before. Parker Solar Probe will keep tightening its orbit in the years ahead. Each pass brings new data about the forces shaping our star's behavior. Ground-based neutrino detectors will keep refining measurements of the fusion chain.
Helioseismology researchers will keep mapping subtle shifts in internal rotation.
Together, these efforts will keep sharpening our picture of the solar core. And they'll keep connecting that picture to stars across the entire universe. Because everything learned here becomes a lens for understanding distant stars too. Stars astronomers can observe but never visit or sample directly. The sun remains our best proxy, our closest real-world laboratory. Every core discovery ripples outward into broader astrophysical understanding. This is the quiet, powerful legacy of NASA's solar research programs. Not just pictures of solar flares or dramatic footage of eruptions, but deep, patient investigation into physics happening far beyond human sight. Physics governing the very light that makes life on Earth possible. It's easy to take sunlight for granted, appearing every single day. But behind that simple daily glow lies a furnace of staggering complexity. A furnace scientists spent generations learning to understand, piece by piece. From Raymond Davis's underground neutrino detector in the 1960s, to international observatories confirming neutrino oscillation decades later, to Parker Solar Probe, flying directly through the sun's outer atmosphere. Each step added confidence to an increasingly detailed scientific picture. And that picture continues expanding with every passing year of research. NASA's investment in this field reflects a long-term vision of discovery. The truth about the sun's core wasn't uncovered overnight. It emerged slowly through decades of instruments, missions, and international collaboration. That patience paid off with a genuinely transformative scientific understanding. An understanding that reshaped textbooks, models, and generations of physics students. And one that continues evolving as new missions launch and new data arrives. The next chapter of this story is still being written right now. Somewhere, a neutrino detector deep underground is quietly counting particles from the sun. Somewhere, a spacecraft is recording magnetic field data near the solar corona. Somewhere, researchers are analyzing sound wave patterns rippling across the sun's surface. All of it feeding into humanity's growing understanding of our own star. A star that, despite being studied for thousands of years, keeps surprising us. A star whose core remains one of nature's most extreme environments. Hotter, denser, and more pressurized than almost anything found on Earth.
taste. And yet, governed by physical laws, scientists have learned to measure precisely. That combination of extremity and precision is part of what makes this story remarkable. It shows nature at its most intense, yet still comprehensible to careful science. NASA's tools turned an unreachable, blinding star into a measurable physical system. Every equation, every detector, every spacecraft contributed to that transformation. And the effort required spanned multiple generations of scientists and engineers. Some of the researchers who began this work never lived to see its conclusion. Their successors carried the investigation forward, building on earlier foundations. This kind of long-term scientific relay is rare, but incredibly powerful. It allowed knowledge to accumulate steadily instead of restarting with each new discovery. And it produced one of the most detailed pictures of any star's interior. More detailed, in fact, than what we know about many objects closer to home. In some ways, we understand the sun's core better than parts of Earth's own interior. That says something remarkable about human ingenuity and scientific persistence. It also highlights just how important consistent, long-term research funding truly is. Missions like SOHO and SDO required sustained support across many years. Without that support, this detailed understanding simply wouldn't exist today. NASA's commitment to solar science reflects a broader commitment to fundamental research. Research that may not have immediate payoffs, but offers deep, long-term value. It protects modern technology from solar storms rooted in that same core activity. It illuminates the physics powering stars throughout the observable universe. And it connects directly to the chemical origins of life itself. Few single research areas offer such a wide range of meaningful benefits. This is why solar physics remains a cornerstone of NASA's scientific mission. And why the sun's core continues attracting fresh attention and new missions. Every layer peeled back reveals another layer still waiting to be explored. From nuclear reactions, to neutrino behavior, to magnetic dynamos, to rotation patterns, each layer connects to the next, forming one unified, evolving story. A story that began with ancient sun worship and simple observation,
and now includes spacecraft flying directly through a star's outer atmosphere.
Few scientific stories span such an enormous range of human history and effort. And few offer such a direct, tangible connection to everyday human life. Every sunrise carries the legacy of reactions happening deep within that core. Every warm afternoon reflects energy released by fusion billions of years ago. Every living cell on Earth ultimately depends on that distant nuclear furnace. Understanding it, even partially, connects us to something vastly larger than ourselves. It's a reminder of how deeply intertwined human life is with cosmic processes. NASA's research didn't just satisfy scientific curiosity, it revealed our own dependence. Dependence on a process happening 93 million miles away, every second. A process invisible to the naked eye, yet essential to everything we know. This is the quiet power behind NASA's decades of solar core research. Not flashy headlines, but steady, meaningful expansion of human understanding. It took neutrino detectors buried underground to catch invisible cosmic messengers. It took decades of sound wave analysis to map the sun's hidden rotation. It took a spacecraft daring enough to fly through solar fire itself. And it took generations of scientists patient enough to piece it all together. The result is a picture of our sun more complete than ever before. A picture showing a core fusing hydrogen at 27 million degrees. A picture showing energy taking hundreds of thousands of years to reach the surface. A picture showing neutrinos escaping instantly, carrying real-time evidence of fusion. A picture showing magnetic fields twisting near the boundary of the radiative zone. A picture showing rotation patterns still puzzling scientists studying them today. Together, these pieces form the most detailed model of a star ever assembled. And that model continues to be tested, refined, and challenged by new data. Because science, at its best, never truly stops asking questions. Even after confirming fusion, neutrino oscillation, and internal rotation patterns. Scientists still wonder about subtle irregularities, hinting at deeper, unknown processes. They still debate whether neutrino output fluctuates with internal solar cycles. They still study magnetic switchbacks captured by Parker Solar Probe's instruments. Each of these open questions represents the next chapter of discovery. And each will likely require new missions, new instruments, and new patience. That patience has always been the true engine behind NASA's greatest achievements. Not a single dramatic breakthrough, but decades of careful, cumulative investigation. The sun's core taught scientists that some of nature's greatest secrets require time. Time to build the right instruments, and time to interpret their subtle signals. Time to send spacecraft where none had ever dared travel before. And time to connect scattered clues into one coherent scientific story. That story now stands as one of NASA's proudest scientific accomplishments. It transformed a distant, blinding light into a measurable physical system. It revealed why the sun shines and how long it has left to shine. It connected nuclear physics directly to the chemistry of living things. And it showed how curiosity, patience, and engineering can unlock cosmic secrets. The sun rises every morning, familiar and unremarkable to most people. But hidden deep within it lies one of nature's most extreme environments. An environment scientists spent generations learning to understand, from 93 million miles away. Every neutrino detected, every sound wave measured, every spacecraft flown added to that understanding. Together, they revealed a core burning steadily, quietly, for billions of years. A core that gave rise to warmth, to light, and eventually to life itself. NASA's journey into the sun's core is far from over. New missions, new instruments, and new questions are already taking shape. But what has already been discovered stands as a remarkable scientific triumph. Deep within our star, humanity found not just fire, but understanding.